Hi everyone, in this video I'm going to talk about wave and how to represent a wave in a continuous space. So I think in the last few classes or videos we have already talked about similar topics, and today I just want to bring a different perspective to introduce it. So hopefully that will give you some more familiarities to this language. Okay. You definitely have encountered linear algebra and the wave, or we say the state, the CAD in many different places. It could be vector, it could be vectors in like a position of velocity. It could be normal mode. It could be some wave functions. So they are all living in the linear space and they all share a similar properties. Okay. So here, when I talk about wave, I mean, for example, this one, like when I say la, like what you are hearing, that la is a wave. Okay. But how do I present this wave either in the x space or in the time space or in the frequency space? It is a matter of your choice. Okay. Some people like to just draw it out and see a wave wiggling, in the real space. Some people like they're playing music, so they care more about the frequency and the wavelength for the sound. So it is a personal choice. And how do we actually carry it out accurately in this real space is what we're going to talk about. So before we do that, I want to recall like two things that you learned back in worksheet 0. In worksheet 0, we talk about the projection operator. Projection operator is an operator that will project my wave. This guy will project on my wave and then find out its amplitude along that specific direction. Okay, this is its continuous space. This is what it looks like in continuous space, and this is what it looks like in discrete space. The biggest difference is that if it's discrete, you will see an I. That I can be E1, E2, E3, E4. Well, X is more continuous, right? Like it can be 1, it could be 1.001, like it could be something like really, really tiny. Okay. And all of this wave, if they live in the linear, if they are a good, live in a good linear space, we can always find a complete set of the basis to spin out my vectors. Okay. If it's discrete, it looks like this. If it's continuous, it looks like this. We also cover this in the video, so I'm gonna avoid repeating myself. Okay, so I'm going to address exactly the same thing we did, but in a slightly different approach. Okay, so let's come back to think about this question. Let's say I have a wave. That wave looks like this. It's an arrow. It's an arrow pointing this way. Okay, so I draw it out here. How many information do you need to describe this arrow? And the answer is 2. You need 2. So to have 2 information, I can choose I can choose 2 bases. I don't need 3, I just need 2. So I can tell people it is 1 in this basis, and the amplitude here will be 1. So 1 in E1 and the 1 along E2 will get me to that vector. Now let's take a look at the projection operator. Let's say if I want to project my wave in this. So what that means is that I want to know what is my, projection amplitude, like how much of my wave side, my vector is along this way. So this cat, meaning I'm going along this direction, right? This one, we expect this one to project on this wave. If you project this on this wave, remember if it's a vector inner product, then E1 dot phi, so that will be E1 strength times phi times the cosine theta, where this is theta. And phi cosine theta, well, E1 strength is 1. So phi times cosine theta will give you exactly the projection, like the strength, the amplitude along E1. Okay, so that's why this is called projection operator, because if you put this on any wave, you essentially find out how much of this wave is sort of projected along that direction. Okay. And then we can do this projection operator along both E1 and E2. So I will know that, oh, this guy has, say, so much along my E1 direction and has so much along my E2 direction. And E1 direction plus E2 direction, that should be one, right? Like this one, if I act this on my wave and then act this on my wave, it eventually just gonna, gonna just like convert it back to my original wave. So this is completeness here. Okay, so now let me work out two questions here. The first question is, how do I project psi on E1 base, like along my E1 direction? Okay, so this meaning, project this, so I can apply my projection operator on this one. And where the meaning of this guy is my amplitude of psi in E1 direction. And then, oh, let me avoid this little hat. Because I want to use it for operator later. Let me do E1 and E2 CAD for the vector here. All right, and then if I ask you to project psi in this E1, E2 basis, how can we do it? This is where you can apply the completeness relationship. So if I project, I can just apply this. I'm a wave function, because this whole thing, this whole complete relationship is one, right? So I can just insert it over here. And then from this expression, it is still psi in general, but from this expression, I can clearly see that, oh, this wave has so much amplitude in E1 direction and so much amplitude in the E2 direction. Okay, so this is amplitude in E1 and E2 direction. And can I try to do other bases if I don't want to do E1, E2, if I want to do F1, F2, I want to do H1, H2, can I do that? Sure, of course you can do that. And you can also construct a completeness relationship for those bases because it's complete, it's a closed space. Okay. I'm going to carry on the same idea, but for a continuous space. So now let me ask you a question. How much information do you need to describe a wave? And this wave is la. Like when I say la, how much information do you need to record that? And the answer is infinite. But essentially, you can think about this. So when I say la, like you know what I'm talking about. But when you really want to accurately record my voice and my information, think about how much information you need. You need to know what I actually sound like at, say, this second. And you also need to know what I sound like at the next second, right? And then the next second, and next second, and next second, and so on, and then 0.1 seconds. Like you need to know my voice at different time. So here I can parameterize my space, or I can parameterize my time such that every moment is an axis. So this axis here, I only need E1, E2. Here to represent this entire crazy shape, I need I need information here, 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 here. And it's infinite. And every little, so for example, at this spot, in this basis, it stores the information of psi of 1, right? And here at 10, at this basis, it stores the information psi of 10. Okay, so this is this. This tells you the basis, right? It is kind of like the location where you store the information. And while this is the amplitude, right? This is the amplitude. So that's why we call psi as a probability amplitude. It's an amplitude. It stores the information of my wave at all this location. So now if I want to know how much information is stored at arbitrary place, it's called x. So what is that? Then naively you'll know that, oh, it is psi of x. Indeed, this is indeed the amplitude. The information stored at this location. But if I want to go back and use because I know this is also, I parameterize it, so now this looks, I can treat it like an infinite dimensional vector. So how do I use the same language? Well, I can project. I can also do the same projection. But now instead of projecting along E1 or E2, I need to project to say 1 cat, 10 cat, 1,000 cat, or some arbitrary x cat. So I can project my wave on this x cat. And where this is the amplitude. So this is psi of x. And this is psi of x. This is what we call the wave function. Like it's a scalar, right? It's a scalar. It's not a vector. Like this phi is a lot. This is a vector. But psi of x is just a scalar, right? Like if you put in 3 in this guy, you will get a number. So it means I have so much information, so much amplitude is located in this position, in this coordinate. Okay. And similarly, I have 2 coordinates, so I have this completeness relationship. If I have an infinite coordinate, then I can do the projection, right? Like I can have infinite summing over the space, and that should be 1 because it's complete. Okay, so now let's try out answering this question. If I want to project my wave and in x, so what I want to know is when I say la, like what is the amplitude of my sound, say when at the time of x or in the position of x. So what I can do is that I can project it on x by doing my projection operator. So this will tell me, say, la, right? Like, so this will tell me, oh, like at say 10 seconds, my sound will be up, like that. So this is this. And then similarly, I can project this in across the entire space by just, like doing exactly the same thing. Like I just plug in this complete relationship, and now it's in continuous. I need to do an integral with a dx here. And again, this is the wave function. Okay. Function is really just an amplitude, telling you how much information is stored at that x position. And if it's another position, it'll be psi of, let's say, 2, psi of 3. Okay. And now you may wonder, how do we represent an operator? So I'm going to give you an example in a discrete space, so it's easier to connect with your prior knowledge. And then I will just mimic it to the continuous space. So for example, I have a vector here. And I want to have an operator, and this operator, what it does is that it will turn this vector into this vector. Like it's a projection along this way. Operators can do many things. It can be maybe rotate my wave by 30 degrees. It can be screening out, all the X information like this one. It can be do a lot of crazy things. Okay. So I'm just taking this as an example. So what I'm saying, this guy, if I translate it in math, is that I am trying to do something to my wave, such that I can get its projection in E1 basis. So this is the idea of what I want to do. But what does it actually look like in real space or in the E1? What does it really look like in E1 basis? How do I actually calculate it with the numbers? It's going to look like a matrix. So let me show you this one step by step. So what does this look like? Here, I'm going to introduce a very powerful trick. So first, I write down the completeness relationship. So I can be 1 or 2. And there's no reason why I need to do I, right? Like I is just my random choice. So this I eventually, it will be sum up. It will run over 1 and 2. So this whole thing is just telling me E1 plus E2 is going to equal to 1. So you can see this I does not mean much. It just meaning it's just an index that of my random choice. It does not affect any value or information outside of this summation, right? Because it's all sum up here at this step. So that meaning if I change I to J and run my J from 1 to 2, and when I expand it, J can be 1 and J can be 2. So you see, this is exactly the same thing. So this I, this J, I can call it K, I can call it H, I can call it anything. It does not matter because eventually it will be sum over and it's not going to affect anything, any variables outside of my summation. So this kind of index does not really have a meaning. This is called the dummy. Okay, this is a dummy index. So how do I make use of this dummy? This is what we want to do. I translate it in math, the more abstract bracket language. And now I want to know what this looks like in real space, right? So, sorry, in the E1, E2 space. So I want to show, like something like a 1, 0, 2, 2, 3. I want to show this equation, but in this kind of format, so it makes sense that I can calculate something. So let me do that. Okay. What I'm gonna do is I'm going to pick up this dummy, the red one, duplicated it and put it here. And this is 1, right? So if I put a 1 times in something, it's gonna just be 1. And this dummy, remember, like we said, this dummy index, the I, no matter how you change this I, after you run through the I will be sum up. So it does not affect any information outside of the equation. Okay, so similarly, I'm going to choose another one with another dummy index. I'm gonna put it here. You see, I just put 2, 1 there, and it should not affect my answer. And I intentionally chose I and J. They are 2 different dummy index. I cannot choose this as I. If I choose this as I may confuse myself because like when I is 1, I will feel like, oh, this need to be 1, 1, and then 1, 1. So I want to avoid that they share the same index. So that's why I choose another dummy index. And I can always do that because, this dummy index will be dealt by its summation before it, carry any information out of that part. If you feel like what I'm saying does not quite convince you, I definitely encourage you to try to expand out the, everything, and then you will see it more clearly once you, do the hard work, finish this hard work. I will also do a little bit here. Okay, so now I do nothing but just like plugging in. Okay. And now once I plug it in, I can start to calculate it. So first I see there's a summation here. So I'm going to move it over to the front. And then there's a summation here. I'm gonna move it over to the front. Okay. So the inside, I have a lot of like a familiar bracket calculation. Okay. So from this step to this step, I did nothing but moving this and this over here. I can do it because it's a linear. And then this is already good. So I'm gonna just like copy that over. Okay, so what should I do next? What I'm gonna do is that here I see there is a number. This number is gonna be related to this operator and also gonna relate to I and the J. Okay, so I'm gonna call this number OIJ. Expand my summation. We have a J index. We have a summation of J that will run through 1 and 2. So this can be 1. And then there's another term that this will be 2. And same for the I. There's a term that will be 1, there will be 2. So if you carefully work it out, then you will get 4 terms, right? Because it can be 1, 1, 1, 2, 2, 2, 2, 1. So you will get 4 terms. Okay. I can't work it out for you, but if this is the first time that you're doing double summations or doing summations, it might worth a little bit time to pause the video and try to work it out, expand this out by yourself. If you do that, you will see this. Okay. Sometimes it takes a little time to get used to this summation and know what can be done, what cannot be done. Yeah, like I'm sure you will understand this eventually. I just want to show you a lot of examples, so eventually it becomes an intuition to you. So if we come back and look at this, you may have seen this in your linear algebra or vector matrices class. What is this? Let's try to rewrite this in my matrix unit. So this is saying I have 0 in E1. I have 0 in E2, but I have some amplitude in E1, right? So now I successfully deal with the right-hand side. How about the left-hand side? Does this remind you of anything? Okay, so let's see. This one and this together tell me the information, what is the amplitude at the E1. Okay. And the way it organizes it, isn't it exactly this guy? Okay, so let's check. For E1 information, I got this term plus that term, right? So if we work out this matrix, it will be this multiplied with this. So we got O11 times E15, that's this one. O12 times E25, that's this. And similarly, you can see this times this will give you this amplitude. So this is what this guy's representation in E1 and E2 space. So this is that mapping. Oh, I have it written down here. I just copy it over. So the summary here is that this guy is this guy's representation in E1 and E2. So O, E, J, E, I. Okay, this gives you a very clear information about you should do, say, 3, going from E1 to E2 basis, or you should do 5 when you go from E2 to E1 basis. Like this gives you very clear information. Exactly. So this is more understandable, but this is more executable. So we can similar ideas. If we carry down the similar logic to continuous space, you can also do this instead of doing this. And you can insert it here. This is what we did in class. And then you will find out that the operator now, this operator, its element, like what it actually do, like each element is gonna also look like this. I would definitely encourage you to go back and look back in our lecture note and see whether those equations now actually speaks to you.